Hi everyone. In another video, I walked through linear search and counted every single one of its operations it performs for its best case scenario and for its worst case scenario. Here's just what this looked like for the worst case scenario, which was we were searching through these 9 cards in an array and we were looking for 11. And as you can see, 11 isn't actually a card in this array, right? So this is the worst case scenario for this implementation of linear search array, in which it has to do 3n plus 4 operations in order to find out that 11 isn't actually in the array. So n is 9, that's the number of elements, the size of our array, and 3 times 9 is 27, plus 4 is 31 operations, okay? Doesn't seem like that much, but this is a pretty small array. So what I wanted to do in this video is take this code right here you see in the bottom left corner and actually compile and run it and show you how you can add a counter variable to keep track of all these values to see what is the number of operations performed for any size array n, and then you can play around with it and actually check your desk check against your algorithm when it runs in a virtual machine or when you run your C++ program. All right, so this is the algorithm here in linear search array that I'm going to head over to my virtual machine, my Linux virtual machine, and show you and run. Okay, so here's the algorithm right here into linear search array. It looks exactly the same as what we were tracing in that other video. So here's what we're going to do. We're going to call linear search array 3 times. One is the best case scenario. We're searching for 7. You can see here's that cards array right here. 7 is the first element. We'll confirm that actually only 5 elements or 5 operations are performed in the best case scenario. Then we'll run it again, which is near worst case scenario. We're looking for 8. 8 happens to be the last element in the array. We'll confirm that 29 operations actually do occur for this near worst case scenario. And then the true worst case scenario, we'll call this function one more time, looking for 11. And you can see 11 is not actually in this array. So let me go ahead and compile this and just run it as is. Okay, so printing out the array, 7, 4, 6, 9, 10, 2, 5, 3, 8. That's the same array that we were using for the cards. Okay, so we're printing out the index for looking for the first item, index 0, which makes sense. We're looking for 7. 7's at index position 0. The next call, we're looking for 8. 8 is at index position 8. That looks good. And then the last one, we're printing out the return value from linear search array looking for 11. 11 is not actually in this array, right? So we see -1, which is the value our function returns if it doesn't find the element target. All right, so here's what we want to do. We want to add another integer variable to this array, to this function called counter. Okay, so counter is going to keep track of all the operations. Okay, so we're effectively going to write code for linear search array to execute that does the exact same thing we were doing manually before for those 3 cases we traced with these red boxes here where we were counting. All right, so I'm going to label everything that we're going to count. So first off, I'm going to do counter plus plus. This is for int I, okay? Now, you don't always have to count the variable declarations, right? But I'm going to be very verbose, so I'm going to count everything. All right, so I'm going to add 1 to counter for int I, and then I'm going to add 1 to counter again. This is going to be for I is assigned 0, right? So here's our for loop. This is the initialization part of the for loop. This always executes once, no matter what, right? So there's adding 1 for I is assigned 0. All right, I less than n. Okay, I less than n. So this is going to execute for each iteration of the for loop, right? Because it's the Boolean condition that is evaluated to determine if the for loop can execute. And then it's also going to execute 1 extra time when I less than n evaluates to false and we break out of the for loop. So I'm going to put in counter plus plus for I less than n evaluating to true, right? If this evaluates to true, then I enter the body of the loop. I'll add 1 to account for that I less than n evaluating to true. Okay, but I've got to add another counter plus plus out here. This is to account for I less than n evaluating to false, okay? So in order for this for loop to exit, right, this eventually has to evaluate to false, and I'm going to add 1 to counter for that case. All right, now I plus plus, okay, this is only going to execute at the end of an iteration to prepare for the next iteration. This is what I like to call the progress towards the Boolean condition being false, okay? So I'm going to put a counter plus plus down here, and this is going to be for I plus plus, okay? I'm putting it at the end of the for loop because I plus plus is going to execute right after this iteration ends. Execution flow is going to transfer up to this spot, our progress towards our Boolean condition being false, and that's when we'll add 1 to counter. Something that's kind of fun, and I'll just mention, if I wanted to, I could actually just put counter plus plus here. Okay, I can put a comma in between all of these conditions, the initialization, the condition, and the progress, to do multiple things at these locations in the for loop. So I could do that if I wanted to, but I'll just keep it outside here to be verbose. Okay, now we're inside of the for loop. We need to account for this Boolean condition here, right? So every time this Boolean condition evaluates, I'm going to add 1 to counter. I'll just write BC Boolean condition. Okay, this is on my if statement right here. Okay, I'm putting it before the if statement, not inside the if statement, because if I put it inside the if statement, then this would only add 1 once, which would be when this evaluates to true and we enter the body of the loop. So I'm putting it before because it's going to execute every time the body of this for loop executes. All right, now inside of my if statement here, I'm going to do, I should do this. I'm going to do a counter plus plus here, and this is for return I. Okay, this is only going to execute 1 time, right? Because a return statement is an early exit from a function. All right, we are almost done, and now we need to head down to this return statement. This return statement also only executes 1 time. Okay, if I don't find the target value, which is the case for my absolute worst case scenario, then this for loop will have executed n times. All I less than n will evaluate to false, so we'll come down outside of the for loop, we'll add 1 for that false Boolean condition, and we'll add 1 for this return statement. I don't want to put this after the return statement because the return statement is an early exit from the function. All right, so I'm going to save this, I'm going to compile it, and let's see, what did I miss? Semicolon, happens often. Compile and run, okay? So now I'm keeping track of my counter, but I'm not displaying my counter, so I don't know the value of it. I need to display the value of my counter right before I return, because after I return this function, counter is going to go out of scope. So I'll write counter, and then I'll just grab this and copy it and paste it, right? I've got 2 possible paths for this function. One is I find the target, I return here, so I got to print out the counter right before I return. The other possible path through this function is when I don't find anything, my for loop executes n times, and I return -1. So I'm going to print out the counter right before I return -1. All right, so our first case scenario, our best case scenario, we're looking for the first element in the array. We're going to perform 5 operations, and that does match our desk check we did in the other video when we were tracing it by hand. All right, and then our almost worst case scenario, when the element we're searching for is the last element, we're going to perform 29 operations. Okay, that does match our desk check. And then the last one is our absolute worst case scenario, when we have to walk through the entire array in order to find out that the element we're searching for isn't actually in the array, in which case we perform 31 operations and return -1. And if we go back to our desk check, this is the last one that I had left coded up here. So 3 times 9, 9 is n, the size of the array is 27, plus 4 is 31. Okay, so here's that desk check, and it's matching our tracing through the linear search algorithm. All right, so I like to do the dash check first and then code up the algorithm and put these counters in to compare. Okay, this is nice because now I can run this searching for any value and I'll see how many operations occur, right? Like for example, if I search for 10, 10 is in the middle of the array, so that's kind of like my average case scenario. And I should expect to see counter be some value in between 5 and 29, right? Because it's not the best case scenario where the element's in the first position, and it's not the worst case scenario where the element's in the last position. So I'll push this code to GitHub. Check out the link in the comment section or in the description of the video, and head over to GitHub, grab the code, run it, and play with it. It's a really great way to understand operation counting, which is the foundation for growth rate functions and big O notation.